Hello students, let us begin our discussion on the artificial variables technique, the BigM method that we will discuss today. So till now we have done problems where the constraints are all less than or equal to type and the right hand side is positive. Okay, so we required only slack variables for getting our initial basic feasible solutions. Okay, but there are certain cases where the some constraints may be greater than or equal to or equal to signs with all right hand side positive. In such problems we have to introduce surplus variables, okay, because slack variables cannot be introduced in such problems. So how to deal with such problems? Okay, so one problem that we face when we introduce surplus variable is this: say x1 plus x2 is less than 5. Okay, less than 5. So here if we introduce this slack variable, and then what we write it as x1 plus x2 plus s1 equal to 5. Okay, and then we put x1 equal to x2 equal to 0, and immediately we get s1 equal to 5 as our initial basic feasible solution. Okay, but if we have a greater than or equal to constraint, the problem that we face is this: we have to introduce a surplus variable. That means we have to write x1 plus x2 minus s1 equal to 5. So in this case, if you put x1 equal to 0 and x2 equal to 0, you get s1 equal to minus 5. But that cannot serve as a basic feasible solution, because feasible requires the solution to be positive. Okay, so that means if we introduce surplus variables, then the constraints become equality. That's not a problem, but we face a problem in finding out the or in getting the initial basic feasible solution, okay, for starting our simplex algorithm. So in such situations, what we do, we introduce one artificial variable. Okay, so we will write x1 plus x2 minus s1 plus a1 equal to 5, and after that what we do, we put x1 equal to 0, x2 equal to 0, s1 equal to 0 to get a1 equal to 5 as our initial basic feasible solution. Okay, so this is where we require artificial variables. Okay, so let me explain here. In LPP, some constraints may have greater than or equal to signs with all bi's positive. That means the right hand side positive. In such problems, we introduce surplus variables in the constraints with greater than or equal to sign. Okay, and most of the time it's not possible to get an initial basic feasible solution directly, just as I have told you, because s1 may come out to be negative. So to avoid this difficulty, we add one or more variable to each such constraint. These variables are called artificial variables. Okay, so these are fictitious and they represent no physical entities. They are just introduced into the equation to get a starting, that is initial basic feasible solution, so that we can begin our simplex table. Okay, so the in any such LPP involving artificial variables, the basic requirement is, or the basic aim is to get rid of the artificial variables as early as possible. Okay, so for this we have two methods. One is BigM method, another is two-phase method. So let us see how BigM method is applied. So in this method we assign a large negative cost, say minus m, where m is greater than 0, is very large. Okay, so m is a very large number, so minus m is large negative number. Okay, so it means actually it's very small number, right? A large negative means its modulus is large but the number is negative. Okay, so to each artificial variables in the objective function of the problem. Okay, so in the earlier problems you have seen that the cost of the slack variables is taken as 0. Okay, but for the artificial variables the cost will not be taken as 0, the costs will be taken as minus m. Okay, minus m, where m is a very large number. So m is so large that, so why is it chosen, we will see. So m is so large that the sign of alpha determines the sign of alpha m plus beta. Okay, so m is taken sufficiently large so that when you get a number of this type, some number alpha into m plus beta, okay, it is positive or negative is determined by the coefficient of m only. Okay, so if we have something like m minus 1000, okay, even then the number will be positive because the coefficient of m is positive. Okay, if we have something like m plus 2000 and another number is say twice m, okay, then twice m will be the larger number. Okay, because the coefficient of m will determine the size of the number. Okay, so due to the large negative cost, the objective function cannot be improved in the presence of artificial variables. So we first remove these artificial variables from the basis matrix by the usual simplex algorithm. Okay, so once an artificial variable leaves the basis, we forget about it forever and never consider its corresponding vector in the further calculations. Okay, so we apply the usual simplex algorithm after introducing the artificial variables, and once the artificial variable leaves the basis, we will not consider it further in the simplex table. Okay, the column corresponding to the artificial variable will be taken as blank. Okay, if the variable leaves the basis. Okay, so several cases may arise. One case is no artificial vectors, means after a few iterations no artificial vectors are present in the basis at some iteration. In this case, all the artificial variables are at zero level. If the optimality conditions are satisfied at this stage, then the problem is solved and it has an optimal solution. If the optimality conditions are not satisfied, then we proceed further, okay, as per the simplex algorithm. Okay, the second case is some artificial variables are present in the basis at positive level even though the optimality conditions are satisfied. Okay, in this case the problem has no feasible solution. Okay, if the artificial variables, at least one artificial variable is still present in the basis, but the optimality condition, that is delta j less than or equal to 0 for all j, is satisfied. Okay, in that case the problem has no feasible solution. Okay, and the third case that may happen is all artificial variables are at zero level and at least one artificial vector is present in the basis. Okay, so it may also happen that one of the artificial variables is still present in the basis but its value is 0. Okay, the xb column, in the xb column you will get the corresponding value to be 0. In this stage, if the optimality conditions are satisfied, then the solution attained is optimal. If the optimality conditions are not satisfied, then we proceed further to get an optimal solution if possible. Okay, so these three cases. So the basic thing that you have to remember is, if no artificial variables are present in the basis and the optimality conditions are satisfied, then the optimal solution has been obtained. And if at least one artificial variable is present in the basis as at positive level and the optimality conditions are satisfied, then the problem has no feasible solution. Okay, so under these restrictions we will start with our computations. Okay, so I have some problems here. Let us consider one of these problems, say the first one. So it's solved by big M method, maximize z equal to minus 2x1 minus x2 subject to this constraint. So you will see here you have a equality sign and here you have greater than or equal to. So for greater than or equal to, you have to introduce surplus variable. Okay, so here you will introduce one surplus variable. Okay, and for the less than or equal to, you will just introduce slack variable. Okay, and what about this? For the equality sign, we usually introduced artificial variable. Okay, in order to get an initial basic feasible solution. Okay, so we introduce one artificial variable here, right? So let us see what we do. So we introduce a surplus variable s1. So we denote the surplus variable by s1, slack variable by s2, and artificial variable. So we require two artificial variable. One is for the equality and another is for the greater than or equal to sign, right? So we need two artificial variables, a1 and a2. Okay, so to get, so what we get these equalities: 3x1 plus x2 plus a1 equal to 3, 4x1 plus 3x2 minus s1 plus a2 equal to 6, x1 plus 2x2 plus s2 equal to 4. Okay, so this is the matrix that we get. So putting x1 equal to x2 equal to 0 and s2 this s2 also we put 0. Okay. Sorry, this surplus s1 equal to 0, right? Putting x1 equal to x2 equal to s1 equal to 0, we get a1 equal to 3, a2 equal to 6 and s2 equal to 4 as our initial basic feasible solution. So we assign a large negative cost minus m to each of the artificial variables. Thus the modified objective function is maximize z equal to minus twice x1 minus x2 minus ma1 minus ma2. Okay, so this is something that you get extra here in this artificial variables technique. Okay, in case of slack variables we did not introduce such type of extra costs. Okay, so here we have two artificial variables, so the objective function will be modified and you have to add this part minus ma1 minus ma2 to the objective function. Okay, next you have to just construct the simplex table with this modified objective function. Okay, so let us see, the system is same as in the earlier videos I had already explained, so today I am not explaining it in the Excel sheet. I have already explained in so many earlier videos, so if you have missed those, please try to see those videos. Okay, so this is the table, simplex table. The first one is the basis vectors, the CB is the cost of the basis vectors, XB represents the values of the basic variables, and X1 is the column corresponding to X1, X2 is the column corresponding to X2. Okay, like that. So if you just fill up these values, initially your initial basic feasible solution contains A1, A2 and S2. Okay, and the value of A1 is 3, value of A2 is 6, value of S2 is 4. Okay, as we have seen just now, we have seen A1 equal to 3, A2 equal to 6 and S2 equal to 4 is our initial basic feasible solution. So we start with this and then we put the values according to this coefficient matrix. Okay, so if you have a look here, the first column is 3 4 1, right? Second column is 1 3 2, third column is 1 0 0. Okay, fourth column is 0 minus 1 1, fifth column is 0 1 0 and sixth column is 0 0 1. Okay, so this is what we get, right? So this is what we have put here. This is the first one, and then you compute. So here you observe the costs. This is minus 2 corresponding to x1. For x2 it's minus 1. For a1 it's minus m. Okay, this is what we have put here. For a2 it's also minus m. Okay, so these two are the extra things. So here you have to write the cost corresponding to a1 is minus m. The cost corresponding to a2 here is minus m. Okay, and then you compute what is CB into YJ. That means you have to multiply the costs. So it's minus 1, first one is minus m into 3 plus minus m into 4. So what is that? It's minus 7m. Okay, and then so it's minus 7m for this one. For the next one it's minus m into 1 plus minus m into 3. Okay, so it's minus 4m, right? So that way it will continue. For the next one is minus m, so it's minus m here. For the next one it's minus m into minus 1, so it's only m, like that. Okay, so you find out what is delta j. Delta j is Cj minus Zj, so it's minus 2 minus 7m. Okay, so it's 7m minus 2. Okay, then for the next one is minus 1 minus 4m, so it's 4m minus 1. Okay, so like that it will continue and we'll get these values. Now see, all delta j are not less than or equal to 0. There are some delta j which are greater than or equal to 0. Okay, greater than 0. So I have to choose the maximum one. So which are positive? These two, 7m minus 2 and 4m minus 1. These are positive because m is a positive number. Minus m is negative, but m is positive. Okay, so we have to select the largest of these two. Which one is the larger? 7m is the larger because m is a very large quantity. The largeness of alpha m plus beta is just decided by the coefficient beta. Okay, so whichever has the larger coefficient will be larger. So 7m minus 2 is the larger one, so we choose we put an arrow mark in 7m minus 2. Okay, so this is what we have done. So this is our incoming vector. Okay, this is the x1 is the incoming vector, right? X1, this is the incoming vector, right? So we find out the minimum ratio of xb divided by x1. So it's 3 by 3, 6 by 4, then 4 by 1. Okay, so the minimum one is this 1. Okay, so this a1 is the outgoing vector. Okay, so this a1 will leave the basis, so we have put an arrow mark here. Okay, this is the arrow mark. A1 will leave the basis. Okay, A1 leaves the basis. So A1 leaves and X1 enters. So in the next step we'll get this. X1 will come in place of A1. What is the cost of X1? It's minus 2. Cost of A2 is minus m. Cost of S2 is 0. Okay, and then 3 is the key element here. This is the key element. So what we have to do? We have to divide the entire row by the key element. Okay. So here the 3 by 3 is 1, this is 1, this is 1 by 3 is 1 by 3. So this particular column we do not do anything because this artificial variable is already out of the basis. Okay, so we don't have to write anything here. So this is what we get by dividing by 3. Next, what we have to do? We have to make this entry 0 and we have to make this entry 0. Okay, so how can I make this entry 4 0? We have to use the elementary row transformation. So R2 will change to R2 minus 4 times of R1. Okay, so this is what we will do here. And for the last one we will do R3 changes to R3 minus R1. Okay, because R3 contains only 1, so 1 minus 1 will be 0. So we will perform these two operations. So once you perform these two operations, you will get this. For the first one, it's this. Okay, so please try to do it yourself so that you can understand. So let me just explain. So it's 6 minus, for this first one is 6 minus 4, yeah, what was that? 6 minus, yeah, 4 into R1, yeah, because here you have 4, so it's 6 minus 4 into R1, so it's 6 minus 4 into 1, so that is 2. 4 minus 4 into 1, that is 0. Okay, so that way it will go. Then the next one also, R3 changes to R3 minus R1, so you will be left with 3 0 5 by 3 like that. Okay, next again you compute what is Zj, that is Cb into Yj, so it's minus 2. Here you see the second column, it's minus 2 by 3 plus minus m into 5 by 3, so it's minus 5m by 3 minus 2 by 3. Okay, and if you just take the difference with this Cj, minus 1 minus 5m by 3 minus 2 by 3, so it's 5m by 3 minus 1 by 3. Okay, so others will be negative here. So here again this is positive quantity, so we have to put an arrow mark here. Our incoming vector will be x2. Okay, the corresponding vector here is x2, so x2 is the incoming vector, and so we will find out the ratio, minimum ratio, 1 divided by 3, 1 by 3, 2 divided by 5 by 3, 3 divided by 5 by 3. Okay, so out of all this the minimum is 6 by 5. Okay, this is the minimum value that we get. So A2 will leave the basis now. Okay, the A2, artificial vector A2 will leave the basis. Okay, so in the next step we will get this, x2 comes in place of A2. Okay, and you have to divide the particular row by the key element. Okay, so what is the key element here? Key element is 5 by 3, so you have to divide this particular row by 5 by 3, so you will be left with 6 by 5, 0, 1. Okay, so please try to do it. And next we have to make these two entries, or the other entries in this particular column, we have to make them 0. Okay, so 1 by 3 has to be made 0, 5 by 3 has to be made 0. Okay, so how to make it 0? R1 will change to R1 minus 1/3 of R2, and R3 will change to R3 minus 5 by 3 times of R2. Okay, so this is what we'll do here. Yeah, so here what I have done, R1 changes to R1 minus let me just see, yeah, R1 minus 1 by 3 into R2. Okay, this is what we have done. And in the next one, what we have done, the third row, we have done R3 changes to R3 minus 5 by 3 times of R2. Okay, this is what we have done. R3 changes to R3 minus 5 by 3 times of R2. Okay, so these are just computations. You do it and you will be getting Zj as -2 -1 1 by 5 0 like that. Okay, and Cj minus Zj. Now you see all delta j are less than or equal to 0. Okay, and no artificial variable is present in the basis. Okay, there is no artificial variable here. Okay, so our optimality conditions are satisfied and no artificial variable is present in the basis. Hence the optimal solution has been reached, and it is given by what? X1, value of X1 here is, you can see in the table, it's 3 by 5, value of X2 is 6 by 5. Okay, so the value is this, and maximum value of Z is -12 by 5. Okay, so another problem, let us you try this problem, you try to solve this problem. Okay, 4x1 plus 3x2 subject to these constraints. Okay, and see what happens. So here you will get need a slack variable, here you will need surplus slack variable, and the last one you will need surplus and artificial. Okay, so it's not that difficult. Let us try another one here. Solve by big M method. Maximize Z equal to 4x1 plus 3x2 subject to x1 plus x2 less than or equal to 50, x1 plus 2x2 less than or equal to 80, greater than or equal to 80, and 3x1 plus 2x2 greater than or equal to 140. Okay. So we introduce, so here you can see for the first one you will require slack variable, for the second one it's greater than or equal to, so you will require surplus variable together with artificial variable, for the third one you will require surplus variable together with artificial variable. Okay, so from the constraint itself you can make out which variables you have to use. So introducing slack variable S1, this is for the first one, surplus variable S2 is for the second one, S3 is for the third one, artificial variable A1 is for the second one, A2 is for the third one. Okay, so we get this equality, x1 plus x2 plus s1 equal to 50. Okay, like that. So we put x1 equal to x2 equal to s2 equal to s3 equal to 0. All given variables and all surplus variables we have to equate to 0. So to get our initial basic feasible solution. So initial basic feasible solution is this: s1 equal to 50, a1 equal to 80, a2 equal to 140. Okay, so this is our initial basic feasible solution, and then we will write this line. We assign large negative cost minus m to each artificial variable. Okay, so the modified objective function is 4x1 plus 3x2 minus ma1 minus ma2. Okay, this is the modified objective function. So now we construct the simplex table. Okay, so as before, b, c, b, x, b. So initially your basis is s1, a1 and a2. Okay, so if you compute here, you will see minus m into 1 is minus m, minus m into 3 is minus 3m, and if you add them up it's minus 4m. So what is delta j? It will be 4 minus 4m, that is 4m plus 4. Okay, so that way the values are calculated, and out of these two, which is the larger one? Here you see the coefficient of m is equal, so the larger one will be the one with the larger constant. Okay, so 4m plus 4 is obviously larger than 4m plus 3. Okay, so we will choose this x1 as the incoming vector. Okay, so it's 50 by 1, 80 by 1, 140 by 3. So this is the outgoing vector. A2 is the outgoing vector. So A2 will leave the basis and x1 will enter the basis. Okay, let us see what happens. So in the next step, A2 will leave and x1 will enter the basis. Okay, x1 enters the basis, and then what we do, we divide the row by the key element. Okay, the key element here is 3. 3 is the key element, so we will divide this by this particular row by 3, and we have to make this quantity 0 and this quantity 0. So how to make 0 here? It's very simple, because both the quantities are 1. So it's R2 changes to R2 minus R3. Okay, and R1 changes to R1 minus R3. So if you do that, you will end up with these values here, and then you compute what is delta j. So here you will get 1 delta j positive or 2 delta j positive. So but out of these two, the larger one is 4m by 3. So we select the 4m by 3. So the corresponding vector, that is x2, is the incoming vector, and then we calculate the minimum ratio. So it's 10 by 3 by 1 by 3, 100 by 3 by 4 by 3, 140 by 3 by 2 by 3. Okay, so that way the minimum ratio comes out to be 10. So S1 is the outgoing vector. So S1 leaves the basis, and in the next step we will get this x2, x2 a1 x1. Okay, so what was the key element here in the earlier step? The key element is this 1 by 3, so we have to divide this particular row by 1 by 3, so we will get this. And then if you have to make this 0, so it's r2 minus 4 by 3 times of r1, and we have to make this also 0. R3 changes to r3 minus 2 by 3 times of r1. Okay, so once you do that, you will get these values, and then compute what is zj. Zj will be this, delta j will be these values. Okay, so here you see all delta j are less than or equal to 0. Okay, but what is the problem? Problem is there is an artificial variable still inside the basis. Okay, this artificial variable a1 is still inside the basis, and its value is 20, which is non-zero. Okay, if the value were 0, then there is no problem, our solution is optimal. But here the value of the artificial variable is 20, so our solution is not optimal, right? And in fact, in this case, there is no feasible solution. The original LPP has no feasible solution. Okay, so all delta j less than or equal to 0, but the artificial variable a1 is present in the basis at positive level. Hence, the LPP has no feasible solution. Okay, so this is your conclusion. So these are the two problems. You please try to do these problems by yourself. So in the next class, I will discuss 2 more problems, and then we will shift to duality. Okay, yes, sorry, the two-phase method. Okay, there is another method of solving. Okay, and these are very important in every exam. This will be asked. Okay, thank you.